Our next talk is from GlobalFoundries. Anthony Yu is Vice President of Computing and Wired Infrastructure, the Computing and Wired Infrastructure Business Unit at GlobalFoundries, where he's responsible for providing differentiated photonic manufacturing services and solutions to clients across multiple industries. Prior to joining GlobalFoundries, he held multiple executive positions at IBM, including Vice President of Semiconductor Technology for Engineering and Technology Services. And Anthony's going to be discussing how silicon photonic solutions address bandwidth, reach, and power challenges, a very timely topic. Anthony, you can go ahead and share your screen.
Thank you, Bob. Nice to see you again. Let me share my screen here. Bob, as I mentioned, with this presentation, we'll briefly cover the silicon photonics solution addressing bandwidth, reach, and power challenges. As we talk about that, I want to emphasize that for this presentation, I'll be showing the perspective of the foundry. We are not an IDM. We are trying to enable the industry to grow in photonics, particularly for the applications that Linley Conference is covering. Over the past year, this pandemic-filled year, we at GlobalFoundries, along with the foundry industry, have seen three megatrends kind of come to forefront in the span of 12 to 14 months. Changes that are probably best described by three megatrends that we're all familiar with as we work from home, recreate from home, and just consume and use volumes of data. The three megatrends we talk about are frictionless networking, virtualization, which basically drives huge demands of storage and computing and acceleration, and hierarchical or artificial intelligence, particularly the computing as it flows from the edge to the core. Underlying those three megatrends, though, are three key trends, what I call key trends, that are kind of pushing photonics to the forefront into the mainstream of manufacturing, which is what brings about our foundry participation. What we're seeing is a divergence within the semiconductor industry of those that are chasing the pure lithographic Moore's law and those that are starting to divert toward more specialized applications, including things like heterogeneous integration and optical interconnect, which Bob, you talked to with the previous speaker at Intel. The second trend is just the explosion of data, the zettabytes of data being driven by mobile applications and mobile connections. And the third one is kind of a more existential threat in the data centers. If you talk to the data center operators, they'll talk about just the enormous consumption of electricity. If you look at various plots of joules per year, you see that if our present electricity consumption were to remain static, and applications such as machine learning and artificial intelligence were to continue, we would be pretty close to consuming all the present electricity today if the computing trend continues at the rate that it has over the last year, and particularly over the last 3 to 4 years. So what we're seeing then is a uptake in those applications that's really driving silicon photonics and silicon photonics foundry to the forefront. On this chart here on the right, you'll see that GlobalFoundries in response has introduced a 300 millimeter silicon photonics foundry platform called GlobalFoundries 90WG. WG stands for waveguide, and that's currently in production today in our East Fishkill facility, what we call Fab 10. The markets that photonics is serving today in our 90WG technology, and primarily in the commercial foundry area, are data center interconnects, 5G, the connection of remote radio heads to the server, and of course, telecom. So most of the volume is of course, the well-known data center interconnect at 1310 nanometer for inside the data center, and also for longer distances, we're seeing C-band photonics at 1550. The growth in silicon photonics, though, is moving quickly into other areas, and those are shown in the 4 boxes to the right, including photonic computing, quantum computing, chip-to-chip interconnect, again, referencing, Bob, your question to Massimo at the last speaker, which is, at what point does the power consumption drive the move toward optical interconnect for short distances? But we'll also see photonics move into things like time-of-flight sensors, automotive LiDAR, and of course, aeronautics. GlobalFoundries was responding to that with our next generation platform. That term is a bit too nebulous for me. So in fact, we are specifically calling it our 45 nanometer technology that can address C-band, L-band, and O-band. And that technology is being installed in our mega fab in Malta, New York, and will be qualified at the end of this year. But as I mentioned, the bread and butter for Foundry today, the volume, the one that's really driving the investment, the proportional investment in R&D and proportional investment in capital is really being driven by what's happening in the data center, which again has been brought about by this incredible uptake in business within the cloud service providers. What I show in this chart here with the orange arrows is where the growth in photonics is happening relative to the data center architecture. So at the very top, this is a familiar core, spine, and leaf architecture. And you can see that as it varies by both bandwidth and distance, in other words, for the connection at the very bottom of the orange arrow, you can see that for data rates of 40 gig to 100 gigabit, those distances are 100 and 500 and being applied in the form of optical transceivers and silicon photonics. Going to greater distances between the leaf and the spine, up to 2 kilometers, we're seeing data rates there of 400 gigabits. And then of course, for the longer distances, 10 kilometer to metro DWDM, we're seeing applications today at 400 gig, and foundries like ours are seeing 400 gig start to morph into early 800 gig silicon photonics. Now, to address the explosion in data and the explosion of computing, particularly driven by artificial intelligence, we are seeing the next wave of silicon photonics will probably be occurring inside the rack. So that's what I have in the gray there, transitioning to silicon photonics, driven by things like chip-to-chip interconnect and very short distance interconnect. And we're going to be seeing photonics occurring within the rack itself. That's being dominated by copper today, and that's the next wave of growth in silicon photonics. So what silicon photonics is it's an application of optics into a VLSI silicon technology. So to do that, fabs like GlobalFoundries, which are largely CMOS based, as you know, we have to change our lexicon of processing and our tool set and our process technology to go from electrons as a carrier to photons as a carrier. I'm not going to go through this in great detail, word for word, but you can see that instead of viewing active devices as transistors, we're now looking for light sources and lasers providing the photons through active devices like modulators and detectors. Instead of dealing with resistors and capacitors, we're now using our VLSI technologies in the fab to build things like waveguides, phase rotators, heaters, and spot size converters. Now, on the bottom right-hand side, we will readily concede that silicon obviously is an indirect band gap material and doesn't have the same material properties as your classic indium phosphide. But the attributes of silicon technology, silicon photonics technology, is what we bring at GlobalFoundries and other foundries by bringing 300 millimeter high volume manufacturing and high level integration of those active and passive devices onto one wafer, bring that about through wide scale manufacturing, high yield, and ultimately lower the cost and lower the power consumption within those data centers. Ultimately, you need that scale, you need that yield, and you need that economy to support the incredible growth that we're seeing, anywhere between 35 to 45% compounded growth rate of silicon photonics transceivers within the data centers, as estimated by people like Yole, Light Counting, and Gartner. So typically what our customers drive with us is our foundry wafers building these PICs. Now a PIC, if you look inside a QSFP type module, which is shown there on the left-hand side, a PIC is comprised of the integration of those active and passive components, such as modulators, photodetectors, and included in there, you would have things like waveguides, polarization splitters, and what the PIC would consist of is either the pure photonic chip, which is only the optical components, or the incorporation, as featured by GlobalFoundries, of RF CMOS onto one chip. So you include the RF TIA and the RF linear driver and the RF redriver onto the same monolithic chip with the photonics, bringing about economies within the QSFP modules as they propagate within the data centers. We feature that in 300 millimeter within GlobalFoundries, and very quickly, if you look at this somewhat crowded chart, but you can see that that's a 100 gig production chip that we have in production today, and it actually has both the TIA and the laser driver CMOS chip, CMOS devices on the same chip as optics. And what we have here is we have a variety of PDK elements supported by commercial EDA providers that have P cells, or think of it as optical I/O blocks, optical ASIC type blocks, which have various modulators, whether it be Mach Zehnder or ring modulators, various types of waveguides, including silicon and silicon nitride waveguides, polarization splitters and polarization rotators, along with several other differentiated features that we have, including passive fiber attach, the option for direct laser attach, and copper pillar and copper receive pads for a variety of packaging technologies. These are the tools that foundries such as GlobalFoundries will offer to, are offering to our customers, which allow them to build and propagate silicon photonics in transceivers, in the data centers today, moving on to the other markets that I showed earlier. Now, the next wave, we believe, of photonics will come with what we call co-package optics. Other people call this in-package optical interconnects, but regardless, what it is it's basically the marrying of the optics, which is typically in a faceplate, or as shown on the left, what's called onboard optics. There you see a top-down view. It looks like modern art, but it's actually a top-down view of a corner of a package showing a high-powered switch ASIC. Think of that as a terabit type of switch on a package. And then there you see at the very edge there, the EO PIC chip, which basically takes the high-powered copper electron-powered electrons and converts it to optics for carrying off the package. What happens as you move to greater and greater speeds, you can't tolerate that sort of distance between the switch ASIC and either the faceplate or the edge of the package. And for co-package optics, for terabit switches, for your next type of AI type applications, you need to have optics virtually next to the switch ASIC, which brings you three things. It brings you power reduction, anywhere between 10 and maybe 100x power reduction, reduces the chip to front panel fan out by bringing the optics right next to, very intimate to the ASIC. And ultimately through technologies like GlobalFoundries, we marry the RF CMOS with the optics, as I showed you before, gives you high bandwidth density and very, very high energy efficiency. Again, trying to lower the amount of consumption of electricity within the data centers. Our technologies, primarily the 45 nanometer next generation technology that I showed earlier, features the following elements within our PDK. From a packaging technology standpoint, because I'll tell you that today that packaging is probably the most important thing we need to cover for this area of co-package optics, our technologies will offer copper pillars and copper receive pads. Our technology will offer, should you choose to pursue it, on-die laser attach, doing laser attach within a cavity on the PIC itself, and then a novel, highly efficient, very tricky passive fiber attach process that employs crystallographically etched V grooves that the fiber slides into, and then the fiber core is directed right into the waveguide with low insertion loss. These are three highly differentiated technologies that we are bringing into our foundry process. Again, trying to bring it to scale in 300 millimeter to allow high yield and economics so that this next generation of photonics can actually take place within the data center. For the photonics itself, what we would call wafer technology, we again emphasize the fact that while we provide things like 2.5D for various chip stacking type options, GlobalFoundries is pursuing a monolithic combined on a chip RF CMOS with silicon photonics, which gives you very high confidence 45 nanometer RF CMOS models integrated with photonics on the same chip. We can bring about different types of modulators, including micro ring modulators, We are one of the first people to actually bring what's primarily a research-driven type of device into production, which gives you high speed, very small size. The diameter there can be as small as 5 microns, high bandwidth density, and again, very high energy efficiency, and silicon nitride waveguides. Now, these are very important because from a photonic standpoint, at a wafer level, the whole issue is link budget, lowering the amount of dB loss as you proceed through a path. That's ultimately going to be the differentiator for this type of application. This is kind of a busy chart, but let me steer you down to the bottom of it. So as you move toward looking at the benefits of the monolithic platform, you can see kind of a typical transmit and receive link at the very bottom of the chart. This is highly simplified. So there you'd have an optical light source at the very end. Here we call that the laser WDM. We've got customers today trying to drive 4 wavelengths. Some of them are doing 8 wavelengths. Some people are doing as many 16 wavelengths per fiber coming in on the transmit side, separating out each one of the different wavelengths with a variety of WDM type structures. Everybody's pursuing their own architectures. And then it comes to the very middle where the transmit output is using an IOSMF. Think of that as our V-groove technology, handling the various fibers coming out of it. It would then traverse through a given distance. And then at the other end of the link is the receive in. So again, at the receive in, you'd have 4, 8, or 16 wavelengths flowing in a fiber, going through a polarization splitter and rotator, and then separated out into the various wavelengths, and then transmitted back into the, stamped back into the electrical domain. The advantage there of our platform of GlobalFoundries is we employ passive fiber attach for high yield fiber, whether it be 4, 8, or 16, and then the monolithic integration of the TIA driver and RF CMOS, including a redriver, into the same circuit. Now, there are various elements of advantages here, and I don't have enough time in this presentation to go through them in complete detail. But thus far, as we've been working with our platform, we're seeing some very specific system improvements. So we're seeing that with the monolithic technology, we can do a higher drive voltage, improving your extinction ratio. And the higher drive voltage, which occurs on the PIC chip, can bring you as much as a 3-order magnitude improvement in your system bit error rate. This allows you, for example, also to reduce the power of your optical source. It's very helpful because of the function of the fact that we can bring on a drive voltage anywhere between 1 to 1.7 volts. And all in all, early results are showing that you can get 4 orders of magnitude of improvement in performance by integrating your RF CMOS onto the same chip monolithically instead of having separate RF chips and separate photonics chip. So in summary, we see industry trends driving photonics. I'll tell you today that from a foundry standpoint, photonics is here. This has been a technology that's been talked about for years and years and years. As the owner of the photonics business line within GlobalFoundries, the demand is real. The orders are in. You've seen that the semiconductor space has seen unprecedented demand. You should take solace in the fact that photonics is real, and customers, and many of you on the call here, are working on photonic applications to address these megatrends that we see and listed out on this chart here. The next wave beyond pluggables, Bob, I believe will be Copackage Optics. That's why I spent a couple minutes here on slides talking about the key component of wider scale adoption. We're ready at GlobalFoundries with our mega fab and our 300 millimeter. We're ready for that next phase we believe is necessary if we continue with this breakneck pace of computing. What will be different here is that I think foundries like GlobalFoundries have to work very closely with our customers, who have to work very closely with packaging OSATs, who has to work very closely with assembly, and has to work very closely with test. This is going to require a new reordering of the ecosystem in order to make this work. I apologize for the difficulties with the production here, Bob, of the charts, but hopefully the message came through, and I welcome any questions.
Okay, thanks, Anthony. If you can go ahead and turn off screen sharing, great. Now I can see you. Okay, I've got some questions. We've got some audience questions, so let's dive in. We've still got some time here.
Good.
I'm going to start off with something really basic for people that aren't familiar with silicon photonics. You mentioned 1310 nanometer and 1550 nanometer, but silicon, in fact, isn't transparent at all wavelengths, right? So sort of a basic question, what's the range of silicon transparency in terms of the wavelengths that can be addressed?
You know, those wavelengths are really kind of driven, I think, by the fibers themselves. We looked at that too, and it's really driven by the amount of dispersion and scattering of the light as it goes through the fibers. Those have been kind of tuned toward the distances and the material of the fiber core, which has been matched to silicon. But obviously, you know, we've got technologies in silicon looking at 1550, 1310, some in between. Below 1310 as well. There is a range of capability there, but you've got to look at it in terms of the quality of the signal as it passes through the fiber itself, which really dictates the range that we're treating with silicon.
Yeah, and I guess importantly, you're able to address standard, basically standard optical interfaces in silicon photonics. So another question that I had was, that you talked about moving from 90 nanometer to 45 nanometer, and you have some new features in 45 nanometer, but is there also a benefit, a shrink benefit in the way we traditionally think about it, or are the optical elements kind of dominated by the wavelength and you can't really shrink them?
Yeah, unfortunately, the wavelength of lights doesn't really scale lithographically either. So that's a very astute question to note. Then when I talk about 90 to 45, Bob, I'm really talking about the CMOS itself. The waveguide thickness may change a little bit. We may introduce some new materials, but the scaling of 90 to 45 really has more to do, at least within GlobalFoundries, for the CMOS itself, not the optics.
Yep. Okay. Let's see, some audience questions here. Is photonics technology able to perform well at a full industrial temperature range? I think, photonics are known for being temperature sensitive. So it's an interesting question.
Yeah, it's those darn lasers. Yeah, I'm not always laughing about that, Bob, but it's been quite a challenge, especially as we move into this area of silicon processing to take JEDEC standards and Telecordia standards and make them kind of talk to each other. There is a particular sensitivity, and there is differences, particularly when you start talking about onboard lasers and temperature sensitivity. I think it remains to be seen how photonics will work in the automotive sector. Automobiles, as well as military applications, have really, really wide ranges of operations. So we'll have to see how photonics withstands that. But it's perfectly suited for the data centers right now, obviously, and perfectly suited for computing environments.
Mm-hmm. Okay, thanks. On the subject of co-packaged optics, I think one of your slides showed an external laser module, but you also talked about on-die laser attach. So what are the trade-offs there between integrated lasers versus external lasers?
Temperature and yield. If you put the laser too close to the ASIC, those ASICs for co-packaged optics get really hot. And you reach a particular range. Again, I don't want to be specific to a laser choice, but proximity heat does not do good things to lasers. We do have people looking at it both ways, but ultimately, I think heat and lasers are a real problem, as well as if you put lasers on the EO chips directly, it makes it a little bit more difficult from a yield standpoint, because ultimately, I think the way that these co-packaged optics will look is you'll have removable EO chiplets at the edge of those switch packages, Bob. So you want to, if one of those goes bad, you want to be able to pull it out and put in the new one. You don't want to throw the whole thing away. So I think having an external laser gives you more manufacturability relative to those EO chiplets.
Right. Okay, thanks. I see an audience question here that relates to one of my questions too, which was connected to the V groove, and basically, precision alignment. So does the V-groove eliminate the need for, high precision mechanical alignment in the assembly process?
I wish. In theory, it makes it easier. It doesn't eliminate it completely. Obviously, crystallographic planes are about as precise as you can get, obviously. But then the insertion of the actual fiber itself, which has got a specific dimension to it, and the placement of that fiber within the V-groove, with or without an accompanying refractive index match material, it makes passive alignment bring about its own set of challenges than active alignment. But I mean, ultimately, I think it's a more manufacturable process. The tooling is incredibly innovative right now to make it work. So I think we will get to a solution, but it doesn't solve all the problems right off the bat.
Okay. And another question on the co-packaged optics topic. Who do you see as partners in setting package standards for silicon photonics and co-packaging?
Well, I'd like to say that the partners have yet to be publicly visible, but I would say that the ecosystem of OSATs, as you see it in the electronic space, are definitely waking up to the reality of the volumes there. So I think you will see many of the same players in the electrical OSAT world step forward and assert themselves as helping to define standards for co-packaged optics. That's happening now.
Okay, thank you. And I think we are out of time, but I believe you'll be available in the breakout. Is that correct?
I won't be, but I'll have a rep there. I unfortunately have a conflict, Bob.
Okay.
But my email is probably accessible through Linley, and I would welcome any follow-up discussions.
Okay, great. Thank you very much, Anthony.
Thank you, Bob.